Okay, this is still exercise 2.8. We're looking at another example. Question 6. It says to sketch y equals 1 plus x over x squared minus 1, showing stationary points and asymptotes. Okay, I'm just going to, we notice that this, whatever this curve is, if you factorize the denominator, it's x minus 1, x plus 1. So we've got two asymptotes, vertical asymptotes at 1, positive 1 and negative 1, but also the whole graph is being shifted up. So there's also going to be a horizontal asymptote here at y equals 1. So what we're going to do, we're going to look for the y-intercept first. So to find the y-intercept, you put x equals 0. And we get that y is 1 plus 0 over 0 minus 1. In other words, the y-intercept is 0. Vertical asymptotes. Remembering that the denominator can't equal 0, so we'll just look and see where the asymptotes are. Factorising x squared minus 1, we get x minus 1 plus 1. X minus 1, x plus 1 equals 0. Therefore, we've got vertical asymptotes that x is positive 1 and x is negative 1. We can look at the behaviour of the asymptotes at around x is positive 1 and x is negative 1. So on either side, we can look at the behaviour of the curve. Okay, so when x is a little bit smaller than negative 1, and we can look at when x is a little bit bigger than negative 1. Also, we can look at when x is a bit smaller than 1, and when x is a little bit larger than 1. Now, if we look at, we know that we've got undefined there at 1 and negative 1. We get negative 1.1, just putting that in on the calculator. In here at the behaviour of the curve on either side of the asymptotes at negative 1, positive 1. All right, what we're going to do next is we're going to find any stationary points. So y dash. Now, if you differentiate 1, you get 0, so we really just need to differentiate that bit over there. So we've got y dash is v times u dash minus u times v dash over v squared. Now v is x squared minus 1. I'm just going to write down what they are here. U is x, u dash is 1, v is x squared minus 1, and v dash is 2x. So we've got v times u dash minus u times v dash over v squared, which is x squared minus 1 squared. Simplifying and collecting like terms, we get x squared minus 1 minus 2x squared over x squared minus 1 squared. And so simplifying that, we get negative x squared minus 1 over x squared minus 1 squared. That's what y dash is. So then we've got for stationary points, y dash equals 0. So negative x squared minus 1 over x squared minus 1 squared is equal to 0. But for that to be the case, the denominator must be 0. Now, taking everything to the other side, we get x squared plus 1 is 0. This obviously has no solution. So therefore, there are no stat points or no stationary points. So we need to look for inflections. So we need to do the second derivative, okay? Now, just looking back up here at our first derivative, so second derivative vu dash minus uv dash over v squared. So v is, just be careful with this, is x squared minus 1 squared. U dash, wait, I better write down what they are here. I'm just going to put them at the bottom of the page here. So for my second derivative, u is negative x squared minus 1. U dash is negative 2x. V is x squared minus 1 to the power of 2. And v dash is 2 bracket x squared minus 1 to the power of 1 times 2x, which is 4x bracket x squared minus 1. Okay, so I've got them down there, so now I can do my second derivative. So we've got v times u dash, now u dash is negative 2x, minus u, now it's minus negative x squared minus 1 times v dash, which is 4x x squared minus 1, over v squared, which is x squared minus 1 squared. Now simplifying this, I'm going to pull out x squared minus 1 as a common factor, and I'm going to pull out 2x as a common factor. So 2x bracket x squared minus 1 is a common factor. So if I've pulled out 2x x squared minus 1, I've still got a negative x squared minus 1 left over. If I've pulled out 2x x squared minus 1, I've got, see, if I go minus negative x squared minus 1, I can really write this as a plus x squared plus 1. So I'm just pulling out a 2 and then the x squared plus 1. Okay, over x squared minus 1 squared. Simplifying this, collecting like terms, I've got 2x bracket x squared minus 1 times, here I've got negative x squared plus 1 plus 2x squared plus 2 all over, over v squared is x squared minus 1 squared squared. So this will be x squared minus 1 to the power of 4, and this is x squared minus 1 to the power of 4. Now coming up here, simplifying our second derivative, we get 2x bracket x squared minus 1. Sorry, you can't see what I'm doing up there. But we will get 2x x squared minus 1. Simplifying this, I get x squared plus 3. So I'll write it up here. So we've got 2x x squared minus 1, x squared plus 3, all over x squared minus 1 to the power of 4. Now, for inflections, the second derivative equals 0. So we've got that all of that equals 0. So 2x x squared minus 1, x squared plus 3 over x squared minus 1 to the power of 4 equals 0. So therefore that numerator has to equal 0. Now, therefore, we've got that x is 0. Now this gives me x is 1 or negative 1, but here the curve is discontinuous here, so therefore there is no inflection there. And here the other one, x squared plus 3, has no solution. So therefore the only solution is x equals 0. Okay? So x squared equals 3 equals 0. X squared plus 3 equals 0 has no solution because x squared is negative 3, and that has no solutions. Therefore, we've got a possible inflection at x is 0. So looking at our, we know actually that when, further up in the question, that when x is 0, y is 1. So we've got a possible inflection at 0, 1. So we need to check concavity. So we've got x and the second derivative, we've got 0. And just looking at a point either side, we can do just a point either side of that 0. To do 0.1 and negative 0.1. Now substituting those values there into the second derivative up here and checking, I got negative 0.6 and positive 0.6, so therefore we have a concavity change. So therefore there is a definite inflection at 0, 1, and it's not a horizontal inflection. So I think we've got enough information there now to sketch this. So we've got no stationary points, and we've got an inflection at 0, negative 1, and we've got some vertical asymptotes at negative 1, positive 1. So we've got a vertical asymptote at negative 1 and a vertical asymptote at positive 1. And we know that we've got an inflection at 0, 1 here. And we know that on this side that the curve is concave down on this side. Also, if we go back up and look at values when x was, just one sec, back here, this is actually positive 0.6 and this is negative 0.6 here. So therefore we've got concave up on the left hand side of 0, so at negative 0.1 it's concave up. Now if we go back and look at the values that we had before, when x is negative 0.9, y is positive 5.7. So that does, so when x is negative 0.9, say here, y is positive 5.7, that fits in with the curve being concave up here on the left hand side of the inflection, and here on the right hand side at say 0.1 the curve is concave down, and if we look at the substituted values for 0.9 we get negative 3.7 if you look further earlier at your working. So this is this middle section of the graph, okay? So we've got an inflection there, but it's not horizontal, so make sure it doesn't look horizontal. Okay, also when x is negative 1.1 we've got that y is negative 4.2, so it's down here somewhere. And when x is positive 1.1 we've got y is 6.2. Now the only thing we need to do is, actually, sorry, I shouldn't be drawing that like that, because I was speaking about, if we look at the original curve, we have a horizontal asymptote. Looks like this is the curve, but the whole thing's been shifted up 1 unit. So we've got a horizontal asymptote here at y is 1. But what I'm going to do, we're going to substitute some large, sorry, I haven't drawn that very well. I might have to do that over the page. And I will do that over the page. So we're going to look at our curve again. And the curve is y equals 1, plus x over x squared minus 1. Now, we're going to look at horizontal asymptotes. So, for large x, we can just substitute when x is 10, or we can find the limit as x approaches infinity. So when x is 10, we get that y is 1 plus 10 over 99, which is, you know, a fraction that's just over 1. It's 1 plus 10 over 99, which is, as a decimal, 1.1 approximately. And when x is negative 10, we're going to get y equals 1 plus negative 10 over 99, which is going to be a fraction slightly smaller than 1. And we get 0.89, or, yeah, actually it's 0.9 to 1 decimal place. So putting all our information together again, we've got that we will have a horizontal asymptote. Therefore, we're going to have a horizontal asymptote at y equals 1. Okay? Now, putting all the information together that we had before, we've got two vertical asymptotes at 1 and negative 1. We have that inflection here at 0, 1. We know that the curve was concave down on the left of that inflection. So this is what we'd drawn before. So we're just going to draw that again. But now we know that we've got the asymptotes at y is 1. We're just looking at that again. So our curve goes like this, and then like this. Now, we know that at when x is 10, it's approaching 1 from above, and we know that when x was, say, 1.1, we had a fairly high value for y. We also know that, say, when x is negative 10, y is approaching negative 1, is approaching 1 from below, it's, say, 0.9, and we knew that for values of x, say, for example, negative 1.1, that we had a large negative value. So this is what the curve looks like, and we have an inflection there at the point 0, 1. Now remembering, the other way to do your horizontal asymptote is to do limit as x approaches infinity. So I'm just going to do that for practice for horizontal asymptotes. Okay, we've got y equals 1 plus x over x squared minus 1, and so the limit as x approaches infinity of 1 plus x over x squared minus 1 is 1 plus, remember dividing everything by the highest power of the denominator, so it's the limit as x approaches infinity of this, which equals, so dividing, we just keep that 1 there on its own, so it's limit as x approaches infinity of 1 plus 1 over 1 minus 1 on x squared. Now, we know that, x on x squared is 1 on x over 1 minus 1 on x squared. So now we can, knowing that the limit as x approaches infinity of 1 on x is 0 and of 1 on x squared is 0, this will be, substituting that in, now we get 1 plus 0 over 1 minus 0, which is 1. So therefore, as x approaches positive infinity, this curve approaches 1, and similarly, the limit as x approaches negative infinity of this curve, 1 plus 1 on x over 1 minus 1 on x squared, same thing for that. When you put negative infinity in there as well, you will get 1 as well. But here it's approaching it from above, and here it's approaching it from below 1. So if you don't want to do the substitution for large values of x, you can just go and do limit as x approaches infinity. Okay? And that's your final curve. That was for question 6. Example, exercise 2.8, question 9. Sketch this curve showing any stationary points, inflections, or asymptotes. Okay, first we'll just look at for the y-intercept, and we'll sub x equals 0, and we'll get that y equals 1 plus 0 over 1 minus 0, which is 1. So therefore we've got the y-intercept is y equals 1. We can see for vertical asymptotes, we can already see that we've got 2. Will be where 1 minus x squared is 0. In other words, 1 minus x, 1 plus x is 0. So we've got vertical asymptotes at 1 and negative 1. Okay, we can, we'll look at the behaviour of those asymptotes a little bit later. Okay, so let's now look for stationary points. So we'll do the first, so this is our function, 1 plus x squared over 1 minus x squared. U is 1 plus x squared, u dashed is 2x, v is 1 minus x squared, and v dashed is negative 2x. So the first derivative, vu dash minus uv dash over v squared, is v, which is 1 minus x squared times u dash minus u times v dash over v squared. And collecting like terms, we get, we can factorize out the, no, there's nothing really to factorize. I wouldn't bother factorizing out the 2x. I would just expand it, 2x minus 2x cubed. Then we've got plus 2x plus 2x cubed over 1 minus x squared all squared. And we end up with 4x over 1 minus x squared squared. So therefore, stat points occur when f dashed x equals 0. So you put your f dashed x equals 0, and therefore 4x must equal 0 because only the numerator there can be 0. And we'll get that therefore there is a stat point, a stationary point at, well, when x is 0, but we already know that when x is 0 from up here, that y is 1. So therefore we've got a stationary point at 0, 1. So we're going to need to determine its nature. So let's look at the second derivative. So just writing out the first derivative again. Sorry, yes. So we've got that u is 4x, u dash is 4, v is 1 minus x squared squared, and v dash is 2 bracket 1 minus x squared times 1, to the power of 1 times negative 2x, which is negative 4x bracket 1 minus x squared. Now we can do the second derivative. So the second derivative is v times u dash minus u times v dash over v squared, which is, I'm going to move that up in this other section here. So the second derivative is v, and I'm just looking further down the page, you can see it on your own page. V is 1 minus x squared squared, u dash is 4, minus u is 4x, and v dash is minus 4x bracket 1 minus x squared over 1 minus x squared squared squared. So we get, this will be 4 bracket 1 minus x squared. Now we've got minus 4x times minus 4x, which is plus 16x squared bracket 1 minus x squared. Sorry, there's a squared there too at the beginning, over 1 minus x squared to the power of 4. Now, this is where we were. I've just written this out while I paused the video. So we've got 4 bracket 1 minus x squared. Then, that's the common factor. There is a 4, and then there's a 1 minus x squared that's in common between the two terms. So that's the common factor. Then we've got bracket. We've got another 1 minus x squared. And then we've got plus. Now we've got the 1 minus x squared and the 4. We still need another plus 4x squared here, all over 1 minus x squared to the power of 4. So that is 4 bracket 1 minus x squared, and collecting like terms here, we've got 3x squared plus 1 all over 1 minus x squared to the power of 4. Now, that's our second derivative. So looking at the nature of our stationary point, when x is 0, we substitute x is 0 into this second derivative. And we get when x is 0, the second derivative is 4 times 1 minus 0 is 1. And then we've got 0 plus 1 over 1 minus 0 to the power of 4. Now that's 4 times 1 is 4 over 1, which is 4, which is greater than 0, therefore concave up. Therefore, we have a minimum at 0, 1. Now, we need to see if there are any other inflections. Now, for inflections, the second derivative equals 0. So here is our second derivative up here. We write that out again, put it equal to 0. Now, we know that the only way that that's going to equal 0 is if the numerator is equal to 0. So therefore, we've got 1 minus x squared is 0, or 3x squared plus 1 is 0. That gives us x squared is negative a third, which has no solutions. But this, you may think that your solutions are 1 and negative 1, but there are vertical asymptotes at 1 and negative 1. So remembering you cannot really you need continuous curves for differentiation. So we've got vertical asymptotes at 1 and negative 1, so therefore there are no inflections at 1 and negative 1. So therefore there are no inflections on this curve. So what we've got basically so far is that we've got vertical asymptotes. This is what we know. Before we go over actually I'll write it over the next page. We know that we've got vertical asymptotes at 1 and negative 1, and we know that we've got a minimum at 0, 1. So I'm going to do that over the page. And I'll write down what the graph is. So the graph is, the curve is 1 plus x squared over 1 minus x squared. We know that we've got a minimum, I think it was a minimum. We've got a minimum at 0, 1. It's what we know so far. We've got no inflections, and we've got vertical asymptotes at x is 1 and minus 1. Remember, we haven't looked at the behavior of those asymptotes yet. We really need to look for horizontal asymptotes as well. So let's look at those. I'm actually going to use the limit as x approaches infinity. So limit as x approaches plus or minus infinity of 1 plus x squared over 1 minus x squared is the limit as x approaches plus or minus infinity. The reason I'm doing plus or minus, we're going to get the same answer because it's x squared, of 1 over x squared plus x squared on x squared over 1 on x squared minus x squared on x squared, which is the limit as x approaches plus or minus infinity of 1 on x squared plus 1 over 1 on x squared minus 1, which is, now we know that the limit as x approaches infinity of these is 0. So we've got 0 plus 1, 0 minus 1, which is negative 1. So therefore these curves, therefore there is a horizontal asymptote at y equals negative 1. Okay, so we can now start painting a picture. Okay, we should also look at the behavior of the curve near the vertical asymptotes. So we can look at that as well. But, yeah, so, okay, I'll just do that now. So when x is negative 1, we know that, just looking up at what the curve is, when x is negative 1, we know that the curve's undefined. So for something a little bit smaller than negative 1, like 1.1, and something a little bit bigger, negative 0.9. So that's 1 plus negative 0.1 squared. Remember, that will be a positive, and this will be positive when you square the negative. So it's just really 1 plus 1.1 squared divided by bracket 1 minus 1.1 squared, close bracket, and you get negative 10 roughly here, or negative 10.5. And when you put in 0.9 squared, 1 plus 0.9 squared, doesn't matter whether it's negative or positive, you're going to get the same answer, divided by 1 minus 0.9 squared, and we get 9.5 here. We're going to get exactly the same answers here, whether they be negative or positive. So for the 0.9, I'll get the 9.5, and for the 1.1, I'll get the negative 10.5. So now we know the behavior of the asymptotes, behavior of the curve around the asymptotes. So let's just put that all together now. So therefore, we've got vertical asymptotes at negative 1 and positive 1. We know that the line y equals negative 1 is a horizontal asymptote. We know that we've got a minimum at 0, 1. We know that when x is positive 0.9, y is 9.5, so it's going to look like that. We know that when x is negative 0.9, using these tables up here, when x is negative 0.9, y is positive 9.5 there. We know that when x is positive 1.1, y is negative 10.5, so we're down here. We know that as x approaches infinity, that y approaches negative 1. Now it must be approaching it from below, so the curve's going to look like that. We know that when x is negative 1.1, y is negative 10.5 down here. And we know that when x approaches negative infinity, y also approaches negative 1, so it must approach it from below. Okay, now the other way, you could have looked at the horizontal asymptotes, or for the horizontal asymptotes, you could have just substituted in, for example, substitute x is plus or minus 10 into your equation, and you would have got that y is 1 plus 100 over 1 minus 100, which is 101 divided by negative 99. You would have got negative 1.02. So therefore, when x is positive 10 or negative 10, it's approaching negative 1, but from below, so negative 1.02, so it's coming from down here. Now that is a lot quicker, I suppose, than doing the horizontal asymptotes this way. Okay, but if you're asked to show that there are horizontal asymptote at y is negative 1, you're going to need to be able to use this method. But if you're just asked to sketch the curve, you can just do your horizontal asymptotes like that. So therefore, here is our curve. Okay. That's the end of the examples for this exercise. I'm now going to set 2 or 3 questions. So you're going to be doing exercise 2.8. I'm just going to set you a couple of questions. I'll just pause the video and just find those questions. Just attempt the following from 2.8. Exercise 2.8 questions 1, 2 and 7. I only want you doing those at the moment. There are other harder ones, but some of those with what are called oblique asymptotes are really for Extension 2 students. So I'll do a separate video on those, and we may spend one more